All right, hi everyone. This is the first example of chapter 4. It is question 48. Let's read the question. Question 48. A 3 nanocoulomb charge Q with a mass of 10 to the power minus 8 kilogram is initially at rest a distance of 10 centimeter from a 5 nanocoulomb charge lowercase q fixed at the origin. The Coulomb force accelerates the uppercase q, so the second charge, away from the first charge, eventually reaching 15 centimeter. Part A. What is the work done by the electric field between R1 and R2? B. What is the velocity of the second charge once it's reached the second position? And part C. Why can we not use the kinematic equation here to find the velocity at the second location? So first, let's start to draw a diagram from the problem. So what we are seeing in the original diagram is we have a charge. I'm going to name that one Q1. It is equal to 5 nanocoulomb. We have a second charge, Q2, which is equal to 3 nanocoulomb. We are told that the first charge is at the origin, so x is equal to 0. The second charge is initially at x equal to 0.1 meter. What happened is these two charges are positive. The first one is fixed. The second one we release it. Because there's a force between them, it will start accelerating away from the first charge. We're going to use the electric potential energy to determine the velocity at the second position in this case. Now, we are given the mass. It's 10 to the power minus 8 kilogram. We are also told that the second charge is initially at rest. That's really important. That means the initial velocity is 0. Also, another important point that we may not notice, this one is fixed in place. If it was not fixed in place, both charges will accelerate away from each other. By saying it's fixed in place, we know this one is not moving. All the energy, or the energy from the potential energy, is then going into that charge in this case. All right? Now the first question is we want to find what is the difference in potential energy from the distance x is equal to 0.1 meter to x is equal to 0.15 meter. All right. So the formula we derive in the last video is that the change in electric potential energy is equal to the Coulomb constant multiplied by the charge of the two charge. And we open the parenthesis, 1 divided by RB minus 1 divided by RA. Like I said in the last video, RB means the final location. The final location, the final distance from the first charge is 0.15 meter. That's the final location. So we enter 0.15 over here. The initial location is 0.1 meter. So we put it over here. Now note, this will give us a negative potential energy of minus 4.5 multiplied by 10 to the power minus 7 joule. Now we are losing potential energy. Now keep in mind that we are creating potential energy when we take two, in this case, two positive charge. We are bringing them together, closer together. There's a force. These two charges are fighting to repel each other. Once you release it, the charge start accelerating. You're converting potential energy into kinetic energy. All right. Now one part I want to come back is this line over here. In this course, to simplify everything we are going to see throughout the semester, we will consider case only where there is no conservative force involved. A conservative force, like friction, add or remove, well, friction remove energy, but a non-conservative force can add or remove energy from a system. Since no non-conservative force are implied, are used here, that means the total energy, potential energy, plus kinetic energy remain the same at all time. The non-conservative work equal to 0. That means the change in energy, now note I use delta E, it's not the electric field here, it's the energy, it's equal to 0. It's equal to the change in potential energy plus the change in kinetic energy. Just like we did in the first semester in mechanics, all right? Now, going back to the part B, if we look at this formula over here, we can take the electric potential energy, flip it on that side, there's a minus. So minus the electric potential energy is equal to the change in kinetic energy. Now recall that the kinetic energy is equal to 1/2 mv squared. So the change in kinetic energy is equal to 1/2 mv the final velocity square minus 1/2 the mass multiplied by the initial velocity square. Or we can simplify it by 1/2 m, open the parenthesis, final velocity square minus initial velocity square. Now note, the initial velocity is 0. It was mentioned in the problem. The final velocity is what we're looking to find here. We are also told that the mass is 10 to the power minus 8 kilogram. So we input all the value, we match the minus of the potential energy. Now note, minus, the minus cancel out. And we end up, once we isolate, with a final velocity of 9.49 meter per second. All right? So it's the same principle we use in mechanic to find the velocity, okay? But we are using energy here. Now, part C of this question is asking, why can we not use the kinematic equation here to find the velocity at the second location? The reason we cannot use the kinematic equation is because the acceleration is not constant. In the first semester, we assume that the acceleration was constant. The kinematic equation breaks down once the acceleration is not constant. Therefore, the easiest way to calculate the location of an object or the velocity of an object at a certain location is to use the energy principle that we developed in the first semester and that we just redefine in this chapter. All right? So we are going to solve many other examples in this chapter. So see you in the next video for another example.